Hi, welcome to the Analog Devices sponsored session at the GNURadio Conference 2021. My name is Robin Getz, and I'm an engineering director in ADI's System Development Group. For those not familiar with analog devices, we operate at the center of the modern digital economy, converting real-world phenomena into actionable insight with a comprehensive suite of analog, mixed signal, power management, RF, digital, and sensor technologies. Analog serves over 125,000 customers worldwide, with more than 75,000 products in the industrial, communication, automotive, and consumer markets. The continuing growth of communications in RF is important to ADI, not only as a separate market, but also ensuring everyone adding wireless technology to their system have a complete ecosystem to lean on, and we're happy to be a longtime sponsor of GNURadio, not only at the conference, but also working on infrastructure and merging new features upstream. At Analog Devices, we invest in our people so they can engineer solutions that sense the real world around us and make it better. Explore jobs where you can find the freedom, training, and opportunity to design solutions that transform the planet. We have lots of openings not only in my group, but in others as we seek the best and brightest talent from around the world. Rather than listen to me talk about things, I'm going to quickly turn it over to a recent ADI intern, David Winter, who is currently a student at Karlsruhe Institute of Technology, where he will describe the project he did during his ADI internship, which started out reaching out to me at last year's GNURadio conference. And with that, I'll pass it on to David.
Hi, and welcome to my talk on OFDM radar and how I implemented an OFDM radar system on a DirectRF platform using IIO and GNURadio. Now, this talk is about DirectRF, so I will start introducing the hardware that I was working with. The boards are what you can see here. To the left, you just have a large FPGA carrier board with a Zinc MPSoC, so that's an FPGA in combination with some ARM cores running Linux. And to the right we have the DirectRF evaluation board that's carrying an AD9081. That's one of the newer 4-channel DirectRF chips. Now, DirectRF means we are sampling at RF frequencies, so we have a 12 gigasample per second DAC. Actually, we have 4 12 gigasample per second DACs and 4 gigasample per second ADCs, though you don't have to sample the first Nyquist band, so the ADC bandwidth is actually 7.5 gigahertz, and you may need some anti-aliasing. To get the data off of the chip, there are 8 JST lanes available, which allow you to transmit up to 200 gigabit per second to and from the device. But in my application, I'm only using around 40 gigabit per second of bandwidth. Now, just a quick primer on how you use DirectRF systems, because 12 gigasample per second is obviously a bit much to handle in an FPGA, at least if you don't want to go crazy. So there are lots of down conversion, up conversion, interpolation, decimation, hardware filters available for you. So in my system I'm using just 250 megasample per second per channel. So I'm running 4 channels. Each of those runs at 250 megasample per second of complex samples in the 2.4 gigahertz ISM band. And I don't really want to run a 2.4 gigahertz numerically controlled oscillator in my FPGA fabric. So all of that stuff is available inside of the AD9081, just needs to be configured, and what you get out of the JST lanes are your downsampled sample streams at baseband. Now, how do samples end up in GNURadio in such a system? It basically works like this, where we have our ADC and DAC over there. Samples are streamed over JST to our FPGA fabric, and in the FPGA fabric we do some sample processing, package those samples in a format that's used by IIO in our kernel, and then we have a DMA in our FPGA fabric that streams those samples into device memory or into the system memory of our processing system. And there we have a kernel driver that hands those sample buffers to an IIO daemon that runs in user space. and that user space daemon then communicates over Ethernet or just IP with GNURadio and an IIO client that's controlled in GNURadio. And yeah, if we take a look at the bandwidth which is involved here, so like I said, we have 250 megasample per channel at 32-bit with 32-bit samples, complex samples. That makes a total of 32 gigabit per second because we have 4 channels. So 32 gigabit per second is a bit much if you try to transfer that over a 1 gigabit Ethernet link. So in this talk, one of the main things I'm going to take a look at is how do we reduce this bandwidth by not making the link useless, because I don't really want to start sending data at 40 gigabit per second or hook up a 40 gigabit per second network card to my laptop, which I don't think it has the interfaces for. The other stages in the data pipeline can carry more than enough data, so the DMA, for example, is probably limited by access to the main system memory, and there we can expect to get like 10 gigabyte per second of throughput, which should be enough. Also, our JST lanes obviously aren't fully used at around 40 gigabit per second with 810 coding overhead. Now, a couple words on IIO. We need to establish what an IIO buffer is and how it relates to IIO devices to understand one of the other issues which are present with IIO. So an IIO context, first of all, represents one system. So your Pluto SDR offers one IIO context, and each context has multiple one or more IIO devices. So an IIO device is then, for example, an ADC, a DAC, or just a clock controller chip where you can control the frequencies of your clocks and so on. And each of those IIO devices may or may not offer an IIO buffer. IIO buffers are used to stream samples. So for some devices it makes sense to stream samples, and for others it doesn't. Which means you can either have an IIO buffer or you don't. So as you can see, the only possibilities are 0 or 1 IIO buffers. But you can't have 2 IIO buffers, which is important because in the case where we have combined devices, like here, that offer ADC and DAC functionality in one device, we can't represent that as a single IIO device. A single IIO device can either have an output IIO buffer or an input IIO buffer, but not both. And why that's important, we will see in a second. Just as an example, here you can see the IIO info output on my AD9081 evaluation setup. So we have a voltage management chip, the clock management chip, the HMC7044 provides the clocks for JST and so on. And now there's the AD9081 IREX device, which controls all the attributes of the RX and also the TX channels. This device is what you can use to stream your input samples from the ADC. So as you can see, this is a buffer capable device, and the voltage 0I input channel, so this is the imaginary part, there's the I part, so in I and Q, so it's actually the real part, sorry. You can use this to stream. When you open this channel, you can stream those samples. And you have another device for the transmit side where you can open this device also in a buffer and stream produce output samples, which are then streamed to the device and into the analog domain. Now, because we only run our link between laptop and device at 1 gigabit per second, obviously we can't saturate the required 32 gigabit per second of data. So what we end up with is multiple buffers, which are in themselves continuous. So there can't be a gap between 2 samples inside of one buffer. And those buffers are always of the same size. You can control the buffer size attribute from most IIO interfaces. So if you've ever looked at the Pluto block in the current GNURadio master branch, there's an option to control the buffer size. And that basically controls how many samples are in one buffer, and by extension also how many samples can be streamed as one block in one continuous fashion. But when one buffer is over, we don't really know what happens. So there may be a gap, there may be no gap. The gap may be a couple milliseconds long or maybe a couple microseconds long. For all intents and purposes, we just don't know when the next buffer is going to come, and we can't rely on any assumptions here. So the first takeaway would be that when we have an OFDM frame for our OFDM radar, we need to make sure that OFDM frame fits into one buffer, and that buffer needs to be large enough to accommodate that frame. Now, large buffers sound scary, but in this case, it's not too bad. The Pluto SDR, for example, has 512 megabyte of DRAM, and in my case, the OFDM radar requires, in a rather large configuration, I guess, a frame size of 260,000 samples. Now, 260,000 samples make up a couple megabytes of samples, which really isn't too bad. Now, the second issue comes from the need to synchronize channels. So it isn't really enough if you can make sure that the transmit data is, or that we maintain transmit data integrity. We also need to fix the relationship between our transmit and receive channels. So this is just an ordinary pulse radar example, where we transmit a pulse and then we measure when that pulse returns. Now, what we are really measuring is the time difference between our transmit and receive signals. But if we don't know when our transmit signal went out of the wire and when it came back, so if we have samples and we don't know when those samples actually arrived, we can't really determine a range because we have no notion of time. So what we really need to do is to introduce a way to synchronize samples between transmit and receive. And one of the approaches to do that in systems where you can stream continuously is just to give your receiver a copy of the transmit signal in the analog domain. So last year, Jean-Michel Free demonstrated this setup where he built a noise radar. He had his transmitter over here and just coupled out minus 30 dB of that signal into his receiver. The receiver correlated the transmit signal that was known with whatever came in on this port, and using that correlation operation, you can basically determine the sample offset in your receive data stream. So when he determines the sample offset, he knows at which point in time that transmit signal exited over here, and using that he can determine the an offset between his transmit and receive stream. But if you're not streaming continuously, which is possible in this case with the B210 because it has USB 3, so even at higher sample rates you can stream continuously. If that's not possible, and if you're using IIO, you will need to introduce some kind of hardware synchronization mechanism. And that synchronization mechanism needs to be very precise, so we need sample accuracy. We don't want any clock domain crossings if you get into the details. So a clock domain crossing may introduce some sample jitter. It needs to be repeatable and it should be configurable at runtime. And this is basically the solution, or rather, this is the problem statement. What you can see here, this is what you would get by default, where we have unrelated transmit and receive buffers. They can start at any time. There will be gaps between those buffers, and we need a way to synchronize those buffers to start and playback and recording together, and to do that in a repeatable manner at a certain repetition frequency. And there's this block, which was also used before, but in a different context, the timing division duplexing engine, which was really meant to be used for communication systems with TDD schemes where you assign certain time slots to certain users. I'm using this same hardware, which already existed with a slightly modified driver, to synchronize my transmit and receiver in a fashion that's a bit similar to an oscilloscope trigger, basically. And thus, just a bit of context, the TDD engine is basically a 24-bit counter. It increases monotonically, and then you just have a couple comparison registers that turn on or off certain output signals. Looks something like this, where we go in this direction with each clock cycle, and once we reach the value that's in the VCO on register, we turn on our VCO channel, and once we reach the value that's in the VCO off register, we turn off the VCO channel, and so on. Those are just names, so there are 3 output channels, VCO, RF, and DP on that device. The terminology is based on how this thing was used in with other transceivers, specifically the AD9361, but they are just names and don't actually mean much. In my case, I'm just using the DP on channel. Now, I built a GNURadio block to control that device, and as you can see, we just tell the RxDMA to turn on at 20 microseconds, and the TXDMA is turned on at a certain time offset T0. T0 can just be controlled using a slider. The TDD engine is integrated into the HDL, as you can see in this block diagram. So we have our ADC sample stream coming from over here. We feed it through our JST layer and into the DMA. And the TDD engine then just blocks that sample stream in front of the DMA and waits until that port goes high. So in this case, we are talking about the Rx channel. Once the Rx channel is enabled by the TDD engine, 1 buffer of data can flow into the DMA and is sent to the CPU, and then the sample stream is disabled again. The same on the TX side. We wait with our TX buffer. So the GNURadio has produced a buffer, sent it to the CPU. The CPU has initiated transfer using the DMA, but the DMA can't output that transfer until we allow it to output that. So it's waiting for the TDD engine. Once the TDD engine gives its ready trigger, the 1 buffer of data is sent to our DAC, and otherwise we just send out zeros. So the output is basically disabled. Before I go on showing you the demo, I would like to quickly introduce OFDM radar and what OFDM radar is all about. Now, I'm sure most of you have heard of OFDM, which is a technique which is mostly used in communications, but OFDM radar is basically what you get when you take that communication technique and its channel estimation capabilities and just take that channel response you estimated to in your equalizer and transform it back into the time domain and basically get the impulse response of your channel back. And this basically allows you to easily combine the capabilities of a communication and radar system. So you know your transmit symbols, which are sent to some other device. The frame looks a bit like Wi-Fi because it's just an OFDM frame. Then you send out your signal. The receiver can receive that data, and the transmitter can wait until it gets a reflection from the receiver or whatever you have in your vicinity. And once it gets the data, that reflection back, and it can do a channel estimation of its own and estimate, get a channel impulse response, and that's basically what we are showing you here in the OFDM radar. That's just a channel impulse response estimation. And there are a couple of advantages to OFDM radar. So obviously it's easy to build communication into it. We have a fairly high processing gain, and it's easy to process if you've ever worked with OFDM. There are also a couple of disadvantages, obviously, in comparison to other radar techniques. It's fairly hard to amplify an OFDM radar signal because we need a very linear amplifier. We have a high peak to average power ratio, not a nice constant amplitude radar signal like with an ordinary pulse or chirp radar signal. and the ranges which we are talking about here are fairly limited, so a couple 100 meters or so. We wouldn't be using this to track aircraft or something like that. And we also have fairly long OFDM radar frames, so we need very high dynamic range capabilities on our receiver if we don't want to get drowned out by our transmitter, because we will be receiving and transmitting at the same time. Now this is a simulation flow graph, which is part of the examples in GR-OFDM radar. As you can see, we just have a radar transmitter, scale that a bit, and send it through a channel model that applies some Doppler shift and simulates 4 targets at AWGN, and send that into the radar receiver. The radar receiver does the OFDM processing and generates a periodogram, which is then displayed in this radar GUI. I can quickly show you this in a demo. So if we run this flow graph, what we get over here is our radar screen, where we have a range increasing when we go to the top. So down here it would be range 0, and then we have 4 targets, each with a different Doppler shift and range. This isn't too interesting right now, but we can get to the demo in a second. The demo setup, which used actual hardware, is very similar. We just have replaced our channel model with an AD9081 sync and source block, and introduced the TED control block, which is used to control the buffer alignment of the transmit and receive buffers, as I explained earlier. This is the hardware setup. The board I showed earlier, now connected to power, gigabit Ethernet to my laptop, and we hooked up some antennas. This is our receive antenna, where we were actually just using one of these antennas, and there are 4 antennas installed here for the DOA capabilities of GR-OFDM radar, but for the OFDM radar demo itself, I'm just using one of those. There's an LNA back here, and those are just connected to our transmit board, which I showed you in an earlier picture. Now, the demo we did here was we used a reflector and just walked back in this area for about 30 to 40 meters. And the result looks like this, where we have very strong coupling between our receiver and transmitter. That's this thing. We have some clutter over here. That's just some trees, iron grates in the ground and stuff like that. Then we have our target, which we can see moving over here. Now, this really doesn't do any fancy radar processing right now. We are not removing stationary clutter. We are not doing any dynamic adjustments of transmit power or something like that. So yeah, that's the demo. A couple words on direction of arrival blocks, which are also part of GR-OFDM radar, because we experimented with those originally with the intent to combine OFDM radar and direction of arrival analysis, but that hasn't happened so far. If you want to learn more about direction of arrival, I recommend you check out Travis' talk at GRCon21 and the Ethos Research DOA module, which I dedicated to DOA analysis. But just for completeness sake, here's the simulation flow graph I used to test my DOA blocks. We have the autocorrelation and subspace decomposition, which is then fed into either the music estimator, spree estimator, and the calibration block, which is just used to compensate for the uniform or the random phase offsets, which may be present in our hardware channels. Now, if we take a look at the GNURadio again, we can see that in this setup, we are just launching the demo. Now we are currently sending at 0 degree, but our system is uncalibrated, which means the results are fairly bad. Calibrate our system, and then we can start changing the direction from which our signal is coming. So if you go to 45 degrees, for example, you can see the spree estimator is spot on, or not spot on, but fairly close. If we want to use this with some real hardware, we basically just need to replace our test waveform generator with our hardware source, combine 4 channels into one vector, and this is it. Though I don't have the hardware hooked up right now, so I can't show you it. In conclusion, the GROFDM radar module implements 2 sets of blocks. The one would be blocks implementing OFDM radar, and the second, DOA blocks. Both of those are independent and both are hardware agnostic, so you could, in theory, implement those with some different SDR. You will need to implement RX and TX synchronization for your OFDM radar blocks. The details are described in the README of that module. Now, regarding the TDD engine, the TDD engine is a really easy way, I would say, to do that synchronization and rather flexible. In case you're working with repeated operations. You could also just make the TDD engine produce 1 frame and then reconfigure it to some other values, but that's not a supported operational mode in the TDD engine GNURadio block I created. What may also be interesting to you is that the TDD engine is already part of the Pluto SDR HDL, but it's not really exposed right now. So you may need to flash a custom firmware, and I opened a pull request which you can build yourself if you want to play around with that, which is available over here. For more information about how the TDD engine can be used with the Pluto SDR, I recommend you check out this wiki article, which will cover more of the implementation details of this entire system. Now, a small outlook for IIO. We plan on introducing some functionality which will make the TDD engine no longer required, I guess. For example, RX and TX timestamping, where we can tell when exactly a buffer was received, and we can tell the system to wait with transmitting a buffer until a certain timestamp. Functionality like GPIO controls, where we can use buffer metadata to set GPIOs to control fast frequency hopping, for example. This could be used to allow certain IIO frames to be transmitted at different frequencies, which may be useful to implement something like Bluetooth or in general fast frequency hopping systems. Then buffer loss detection, especially on the receive side, we really can't tell if a buffer has actually been received right after the last one, or if there's a gap in there, and so on. So especially when we've got RX timestamping set up or up and running, buffer loss detection should be a lot easier. And also we are working on speed improvements. So currently the network protocol, for example, is a synchronous protocol which just doesn't really cut it and has quite a large processing overhead. Now again, a couple links. Like I said, the wiki article may be interesting if you're looking for more of the implementation details, just GROFDM radar. And if you want to learn more about the AD981, there you go. Thanks for your attention, and I will be answering questions in the chat.
Thanks very much, David. We're definitely going to be hanging around the chat to answer any questions. And if you're interested in future positions, whether it's full-time or internships at ADI, definitely reach out. Thanks a lot.